So I'm going to talk to you today about rotation-age relationships. So this is gyrochronology, and that's the idea that if you measure the rotation period of a star, that you can use that rotation period as an indicator of how old that star is. And this has been an idea that's been floating around for a long time, and I'm going to talk to you about the steps we've been taking to turn it from an idea into a tool that can be used by a broad community of people. But also, as we've worked on turning this thing into a tool, we've stumbled across a lot of problems, and those problems have actually revealed really interesting trends in the ways that magnetism in stars evolves as a function of time. Okay, so this whole thing is motivated by the fact that having ages for stars opens a lot of windows for things we can do. Right, so if we are studying the Milky Way and we're looking at the kinematics of stars in the Milky Way or galactic chemical evolution or the formation history itself, having a way of measuring an independent age for stars in the Milky Way gives us the means to really study these trends separately, right? Same is true for exoplanetary systems. We have all of these dimensions that we can explore: mass of the exoplanet, radius, host star type, host star irradiance, all of these things, activity, environment. The dimension we really don't have that much information on is age. And we'd really like to know whether the kinds of planets we see around stars vary as a function of time. Do you have radius evolution as a function of time? Do you have system architecture evolution as a function of time? And for that, you need an independent age for the star. So ages are hot right now. It's something everybody's going after. There's lots of different techniques for doing it. The one we're going to focus on today is period-age relationships. So I like showing this diagram to motivate why we're so interested in this tool. Every line on this diagram is idealized. So what you're seeing here is for a 5 billion-year-old star at a range of different masses, what is the age precision in billions of years that you can get from different techniques? So the two curves that are labeled parallax here are basically isochrone fitting, right? So saying this is how well I can place an object on the HR diagram. They are idealized in the sense that here we've assumed you know the luminosity and effective temperature perfectly, which is decidedly not the case, and that the only uncertainty you have is 0.05 or 0.1 dex uncertainty in metallicity. And you can see you do fine for something like the sun, but this blows up to errors larger than the age of the Milky Way very quickly as you go to low mass stars. And that's simply a statement that these low mass stars are aging very slowly, right? Their surface properties aren't changing. And this really is not the tool that you'd like to use to get ages for those systems. Astroseismology does better. We're going to talk about why that is. But basically what it gets you is a diagnostic of the core. And the core is changing as a function of time, even if the surface is not. And so essentially what you get from seismology in terms of age error is a fixed fraction of the main sequence lifetime is your uncertainty in the age. The mass period age relationship down here is looking better than anything else on this plot. Also idealized, assuming that you know that relationship, which we do not. But if you assume a relationship and you assume the only thing you don't really know is the initial rotation period of your star, you get an age uncertainty that is very low across a wide range of masses. And so this is why we are so keen on trying to understand this, because it has the potential to be a better age diagnostic than anything else for, in particular, low mass stars. All right. So we've known, yes, Ruth.
Just what's the cause of the blow up in precision when you go to
here?
Masses, right?
Yeah, so this is just that low mass stars remain, basically have a memory of their initial conditions for much longer. It can take, they take a long time to spin down in the beginning. And so for a sun-like star, you end up, and I'll show in a couple of slides how this evolution happens, but for a sun-like star, you end up basically converged so that there's a single period at a given time by, 0.5 billion years. For a low mass star, that can take 3. And so this is basically, you just, for a long time, when you only have 10 billion years of time in the galaxy, and this is only a 5 billion-year-old star, you haven't been spinning down enough to have forgotten your initial conditions. Any other questions? Okay, I love being interrupted, so please do. We've known for 50 years that this happens. We know that rotation period declines as a function of time. So Andy Skumanich, coming up on 50 years this year, notice that when you looked at the rotational velocities of open clusters, that the older the cluster was, the slower the stars were spinning, and that rotation period increased as the square root of age. Right, and the reason we think this happens is that these stars all have convective envelopes. It's convection in the presence of rotation that drives the magnetic dynamo. That magnetic field interacts with mass loss from the star and provides a lever arm by which that mass loss can carry away a large amount of angular momentum. And so even with something like the solar wind, you can lose and shed angular momentum as a function of time. Okay, so I'm going to show you this. This is also not real. This is a simulated open cluster. So I've initialized this thing. This is currently about the age of the Pleiades. I've initialized this with a range of initial rotation periods, which is what we expect from a cloud of material that forms stars, right? Not every star is going to have the same period when it starts. You have of order 2 orders of magnitude in spread in that initial period, right? And I'm going to play this guy forward in time and let you see how that evolution we think should look. Yes.
When you say you have 2 orders of magnitude in spread of the initial period, that's far larger than the spread in the initial radius? Or can I think of it if I express the initial rotation period as a fraction of the breakup, it would be fairly constant at like some high fraction of the breakup?
Let's see, you should think of it as, it's not necessary because when you should think of it as a spread in the amount of initial angular momentum imparted to that star. And then as if you're are you talking about like pre-main sequence contraction? Is that what you're concerned about?
And you contract and accrete, do you basically stay very close to breakup? You're always trying to shove mass on, but you can't.
Right.
Until you shed some.
So you would think that you would, and the naive expectation is you would be close to breakup. What actually happens, we think, is that stars interact with their disks. And so they magnetically lock to their disks. And so you actually see that they're not rotating anywhere near breakup until you go to the very high mass stars. And so that initial rotation distribution is basically, you should think of it, once I've reached the ZAMs and I'm done contracting, I have 2 orders of magnitude spread in my periods.
Nice.
Yeah. So this is 2 things you should be noticing. Now this is played a couple times, is that everything slides to longer rotation periods at later times in a way that's very measurable, right? This is the y-axis here is logarithmic. This is not subtle. This is the difference between a few days and many, many days. The second is that spread that we had early on is disappearing as time goes on. And it happens first in the hotter stars and later in the cooler stars. And this is just a statement of what we think the angular momentum loss, how it depends on the rotation velocity. So we think it's an omega cubed thing. So the faster you're spinning, the more angular momentum you lose. So fast stars spin down fast, slow stars spin down slow, and you end up with things that are forced asymptotically onto this tight sequence. Where here, asymptotically for a sun-like star is already kind of in play by 0.5 billion years. The tighter this is, the better an age diagnostic it is, right? You need it to be that there is a direct one-to-one mapping at a given time for a given mass to a period. The more scatter, the worse the relationship gets. Yeah.
Don't open this can of worms yet, but these are all single stars?
These are all single stars. We can open that can of worms later. Well, in the questions later, I'm not even going to touch binaries. They cause all kinds of problems. But yes, this is for single stars. And the last thing is there's some mass dependence to this, right? So I can't actually just have it be period age. It's a period age mass relationship always. There's always some term in there that depends on the mass of the star. Okay. All right, so you could say, well, fine, that's a nice model and it has all these nice properties. Does it actually look like that in nature? And I'm going to convince you with a couple of open clusters that it does. So I'm going to show you a sequence of open cluster stars. So all those stars in that cluster are coeval and the same composition. I want you to pay attention to those 2 things, the motion of periods on the y-axis, right, going to longer period, the convergence of that sequence. Try to ignore the fact that the coverage of any given cluster in effective temperature is not going to be the same from cluster to cluster. That's purely detection bias and survey strategy, and it has nothing to do with the actual physics of the problem. Okay, so very young. This is now Pleiades age, this one too. Now we are at, this is M37 at 500 million years. Price it be at something like 0.6 to 0.8. NGC 6811 at 1, 6819, and Ruprecht 147 at 2.5 to kind of 2.7, and then M67 at 4. So those two things are present, right? You start off with a wide range of rotation periods that narrows down onto a tight sequence at late times very nicely. The scatter here is very low. It's consistent with basically a 10% age error is what you'd get from this kind of scatter. And that you have real measurable and obvious period evolution as a function of time. Okay, so.
It looks like your scatter increased for M67.
It's because the measurements for M67 are not very good. The data for that particular cluster is not a whole lot longer than the rotation periods you're searching for. It's only about a factor of 2 longer, and that's why there's. If I had plotted the error bars on it, you wouldn't be worried. They're actually quite large. Okay, so you can approach this problem in 2 basic ways, and we do in the literature. There's the fully empirical approach, which says we're dealing with mass loss and magnetic fields, and that makes us uncomfortable. So let's just let nature tell us what's going on. So let's go out, measure my rotation periods for stars whose ages we can figure out some other way, because they're cluster stars, or you have asteroseismology, or they're in a binary, or the sun, and then just calibrate some relationship. These relationships often, but don't always, follow a form similar to this, where it's some kind of power law that depends on time, some kind of power law that has a mass dependence to it, and then you just go ahead and fit the thing. I sit more in the semi-empirical camp, which says, well, we have some ideas about how this relationship should vary as a function of stellar properties. We know from stellar models what the convection zone should be doing. We have some indication of how magnetic field should scale with things, some indication of how maybe mass loss scales with stellar properties. And even if we don't know for sure, we can surely choose a relationship, bake it into this, and then see if it works. So here we choose some functional form, but we still leave fudge factors basically in there so that we can tune it so that it matches what we actually see in nature. Nobody ever gets this right so far from first principles. You always have to tune it to match. So in either case, we're heavily reliant on the sources that we have as calibrators, which are these guys, right? So this is probably the majority of the calibrating stars out there are probably on this plot right now. There's a few more, but most of them come from the open clusters. They're the gold standard. This looks pretty good when I show it to you in this space, but if I switch it to an age effective temperature diagram, where each open cluster is now a horizontal line, everything's at the same age, it looks a lot worse, right? There's a gaping empty spot that accounts for more than half the age of the Milky Way, and it gets worse as you go to low mass stars. And this is basically purely a statement that old open clusters are rare, thus distant, thus hard to study. And so studying that open cluster from the cluster standpoint and also measuring rotation periods in it gets really challenging. And so we just don't have many calibrators out there. So in order to fix that, there have been 2 major missions that have really changed the kind of landscape for this in the last decade. The first was Kepler, second is now TESS. Both of these guys are designed to find transiting exoplanets. It turns out if you build a mission, actually either in transits or RV, that is designed to find Earth-like planets around sun-like stars, you've built a mission that's exceptionally good at detecting any kind of stellar variability. So the 2 things that these open is both the ability to wholesale measure rotation for lots and lots of stars, and also to do asteroseismology of stars to get very precise ages. So on the rotation side, what you're looking at is you're looking for spot modulation. So you have a spotted star that is rotating. The spots are dark in contrast to the photosphere. And as that star rotates and the star spots rotate into and out of view, you get a modulation on the time scale of the rotation period. Simple. Now, in reality, what you're looking at is a star that has spots that are emerging, decaying. They're at some active latitude that maybe is not rotating at the same rate as the equatorial rotation period, right? Because you have differential rotation. And you maybe have an activity cycle, so maybe you don't have spots all of the time, right? So in practice, interpreting what you're seeing in a modulation signal, as people here know well, is challenging. But in principle, you can go and just go ahead and measure this modulation signal, and it is least closely related to the true equatorial rotation period of the star. So this is what it looks like in Kepler. This is a 14-day rotation period over almost 10 times that amount of time. This really jagged wiggling you're seeing is the rotation signal. You can see some of what I said is present here, like the amplitude is not constant throughout the entire light curve, and that's probably spot evolution at play, right? You just happen to have spot patterns that give you a larger amplitude at some portions of the light curve. But this is relatively easy to measure rotation periods from, and then we get many, many tens of thousands of objects with measured rotation periods. The sun is shown here. And this is actually a good point to kind of give an aside and advertise some work that we've been doing. So almost all of the results I'm about to show you throughout this entire talk come from Kepler and not from TESS. And those of you who work on TESS might be wondering why. Those of you that work on rotation and TESS know why. It's that rotation periods have been extremely difficult to extract from the TESS mission. It's got a 14-day orbit, which gives you a 14 and 27-day alias and systematics in the light curve that are very hard to get rid of. It's not like a transit where you get some clean, relatively clean kind of boxcar type feature. This is sinusoids that you're trying to pull out, so it's hard. So I have a graduate student at UH who has been working on extracting rotation periods from TESS. He's approached this problem by taking models of what that spot modulation should look like that are modeled with the full complexity of what we think spots are doing on stars, injecting them into TESS light curves, and then using a neural network and training the neural network to recognize the rotation period against the really ugly background of the TESS systematics. And as of a couple weeks ago, he's starting to produce his first rotation periods. You can see they do not look terribly different than the rotation periods in the Kepler field, which means we're probably on the right track here. So I hope that the things I'm going to tell you today about what we've done in the Kepler field, we're very soon going to be addressing the same kinds of problems with stars across the entire sky and opening this up not just to one window in the galaxy. Okay, but the takeaway is we have a lot of rotation periods. So the thing we need is ages to fill out this diagram, right? And that's where the astroseismology comes in. So astroseismology of sun-like stars is the detection and modeling of pulsations. So these pulsations are stochastically driven by convection in the outer envelope. They're also intrinsically damped. So at any given time you view a star, you're not necessarily seeing the same pattern of oscillation modes. You need to sit there and stare at it for a while. The modes that you excite a broad range of frequencies from convection, right? Because convection spans a broad range of frequencies. Those frequencies that are resonant in the star are long-lived, and those modes survive for a long time. Those that aren't get damped out fast, and you end up with a set of standing waves in the star that are acoustic in nature. And you can describe them in terms of spherical harmonics. So we'll often refer to these modes in terms of their L, N, and M quantum numbers. And the mode itself, the wave itself lives throughout the interior of the star, but what we detect is the motion it causes at the surface. So you can either directly detect that motion in RVs, so you're talking of order 10 centimeters a second for a sun-like star, higher if you go to higher luminosity stars, lower if you go down the main sequence. Or you can detect it in intensity, where as that material is compressed, the temperature increases, the intensity increases, and you get flickering from it. This video that has now stopped playing was RV detection of the characteristic 5-minute oscillations on the sun. Okay, in intensity and in Kepler, it looks like this. This is the poster child of astroseismology in Kepler, 16 sig A. Notice the y-axis is the micromagnitudes, tiny signal, right? But very clearly, if you zoom in on this, you can see it's coherent. It's not just noise. This is all those stochastic oscillations, many, many oscillation modes simultaneously viewed in the light curve. We take this, we take a Fourier transform. We have to remove the background from convective granulation, but that's a smooth thing. That's just fit out. And what's left is the power from solar-like oscillations. So you get not just some forest of peaks, but a really regular pattern in sun-like stars because you do drive the interior at all these frequencies from convection. It excites a broad range. And you get this envelope of things that are excited, where the frequency that envelope peaks at, we call nu max. It's the frequency of maximum power. You can show with relatively simple scalings that this should scale with the surface gravity of the star. So the bigger the star, the lower the frequencies it brings out, which makes sense, right? If I zoom in on this, same star, now these modes are labeled by their degree. So this is, degree 0, 1, 2. There's a characteristic spacing that you see that's the immediate thing your eyes snap to. That's what we call delta nu, the large frequency separation, can show through similar arguments that this is actually just the sound crossing time in the star. It's just the dynamical time. So it's related to the square root of the density of the object. But the thing we really care about from the standpoint of ages is this one here. So if we look at this thing that's labeled little delta nu, which we call the small frequency separation, really creative naming scheme, between these modes here, these guys are almost degenerate, but not quite. And what's going on here is you have two modes. The L equals 0 mode goes right through the core of the star. The L equals 2 goes through almost the same portion of the envelope, but just turns shy of the core. So one goes through the core, one doesn't. These are acoustic, right? So they care about the sound speed. As you burn hydrogen into helium, you both change the structure of the core and the mean molecular weight, both of which change the sound speed. And so this L equals 2 mode, this L equals, 0 mode feels that change in sound speed and has a different frequency than the L equals 2. And so as the star ages, the separation changes and it gives you a way of measuring age. And these are precise. You can get ages that have fractional age uncertainties of less than 10% this way. This is a random uncertainty from just the model, assuming a fixed stellar model, right? There's a systematic component to this that's probably of order 10%. That is, what input physics did I put into that stellar model to begin with? That is a problem in every age scale ever designed, basically, apart from the age of the sun, right? Is what systematically did I assume in my input physics for my stellar models? But these are good. And it's good in a way that most other age indicators aren't, right? These guys out here are not the oldest stars. They're actually the youngest. They're F stars whose modes are a bit fuzzier and harder to measure. All those old stars that we really want precise ages for are living over here. All right, so you could say, where do the seismic targets from Kepler live on this diagram? They live here. You probably have two reactions to that. One is, why aren't there more? There's only like 20 things on this plot. And the reason for that is that you really do need an extremely bright star. You need to have looked at it at kind of minute cadence for a year or more for most of these cases to get a really good, that small frequency separation needs you to stare at it for a long time to get the resolution in Fourier space to detect it, right? So you end up with not too many stars that are both bright enough and have been sitting on silicon long enough to have the data that you need. This, yes?
Can you predict those frequencies well enough that you could do a very targeted observing campaign at a very definite cadence from the ground?
Yep.
Because if I know that there's two sharp sinusoids with a small frequency difference, but I know their intrinsic frequencies well, I only need the bandwidth to resolve the difference.
Yeah, it's remarkably well predicted. So even before Kepler launched, they had a prediction for what they would see, and they were basically spot on in terms of like detectability of modes and where they should show up.
But that means if you've got the right 5 nights out of the year, you can measure the small frequency spacing in any star that you can get from the ground.
I think it's worse than that because they're stochastic, remember? So your amplitude is not always, you're not necessarily always going to see that mode on that night. So I think we could be clever about it, but I think you need to account for that stochastic nature. Yeah.
I mean, is the precision sufficient from the ground?
Yeah, if you do it in RVs. So
Okay.
our RV is the place to go. It's actually, if an astroseismologist could choose a data set and didn't have to pay the cost of what it costs to collect that data set, we would always choose RV. The convective background noise is way lower in RV. And we can get, one of the problems we have is we only detect low degree modes, which are actually the best ones for most of the things we'd like to study. But there's some really nice information you can pull out if you can get to L equals 3, and you get partial cancellation of those modes on the surface if you do it in intensity that is not quite as bad in RV. So RV you need a big piece of glass, fast readout, high resolution spectrograph, and patience, and you'll get it. And it's been done. Beautiful power spectra. Yeah, excellent questions. Okay, so the second thing you might notice is like this doesn't span the whole temperature range, right? You really have pretty sharp cutoff at 5,000 degrees. That's purely a statement that the amplitudes of low mass star pulsations are lower. It scales very strongly with luminosity. And so these guys are just beyond the range of Kepler's photometric precision to detect. The lowest mass stars we really have asteroid seismology for are like 0.8 solar masses. There's no reason to think we can't get down below this and reach the K or M dwarfs, just don't have the precision. I also wanted to add, in terms of predictability of oscillations, you have to worry about magnetism. That's another thing, is if it's a very magnetic star, it may suppress your pulsations. Okay, so this is what we've got. The thing that we do get that's excellent is around solar, where most of our effort has been put in to understand this. Suddenly, we now have a range of ages that spans the age of the Milky Way. That's the first time we had that. So let's compare this to the model. So what I'm going to show you here, there's too many dimensions to this problem, so it's going to be a movie again. This is period-age relationship in a slice of effective temperature, which is a slice in mass. And we're going to sweep from higher mass stars to lower mass stars. The points are clusters, so now there are vertical lines of stars in a cluster, and the gray background lines are models. And so you should be comparing how well those points sit against the models. Okay, so not perfect, but not terrible. It better be pretty good because these models are calibrated to some of these points. And if we weren't matching them, it would be pretty embarrassing, right? So it's designed to look okay. Now what I'm going to do is add on the astroseismic targets. They're now in red. Same deal. Pay attention to the same matchup. So particularly here, right, you can see that there's a clump of points that shows up that's sitting and rotating at rotation periods that are much faster than the models predict. And it shows up kind of at solar temperature and late ages is where you really see the discrepancy. And Ruth was the first person to point this out. She looked at the seismic sample and the cluster sample and said, hey, these guys are not following the same period-age relationship. It is very hard with any of these breaking models, in fact, impossible unless you change something, to get something that simultaneously matches the clusters and the astroseismology without changing something fundamental in the model. So we said, okay, what could we change?
Just ask the question.
Yeah.
Looks like for at least in early phases, or well, I guess you're scanning through temperature there. Is that what you're doing? At some temperatures, you have multiple, you have more than one period for a given age. Is that imagining that, or do I see? Like at the early, I see like the lower temperatures, higher temperatures. I guess you go. Yeah.
These guys here.
Well, no, at the late ages, looks like there's more than one period for a given age.
So
in the curves, not in the points.
Yeah. Oh, in the this.
Yeah.
That is basically it's an artifact of the way I made the curve. Some of them are truncated at a particular evolutionary point, and other ones are allowed to go up the RGB. So it's just an artifact. Okay. So we said, all right, what could we change about the magnetic breaking law that might give us a better way of doing it? How can we make it fit both data sets? And whenever we talk about magnetism in stars, we almost always find ourselves coming back to this number. This is the Rossby number. We form it by dividing the rotation period divided by a typical overturn timescale in the convection zone. And it's because we think magnetic dynamos should care about both rotation and convection. It's a combination of the two. It's when those two timescales are similar that they maximally interact and drive your dynamo action. You can think of this also as a measure of the importance of the Coriolis force on convective elements in the convection zone. Over time, Rossby number tends to get larger. So a sun-like star over its life, while it's on the main sequence, this number doesn't change a lot because its convection zone stays the same size, but the rotation period's getting longer, so Rossby number goes up. This guy, while it's fixed for a given star on the main sequence, is a very strong function of mass. So high mass stars have short overturn timescales, low mass stars have long ones. So that's a way of baking in a mass dependence that's very natural to the problem. Okay, so what we said is, let's imagine that we take a standard spin-down model for a sun-like star at solar composition that would look like this. And we let that standard spin-down model do its thing up until some given critical Rossby number. Once it hits that critical Rossby number, we turn off angular momentum loss. We say something happens to the dynamo, something happens to the field that makes angular momentum loss very inefficient. We don't say what it is, we just say something happens. And we let that star evolve, conserving angular momentum. This curve is almost flat, and it's not perfectly flat because the star is expanding as it ages. And so even though it's conserving angular momentum, the period is drifting longward, but it's doing so much more slowly than it otherwise would have. And then we can choose what critical Rossby number we pick, and that picks where this peels off that standard relationship. And we can basically fit for this parameter and say what critical Rossby number would do a good job of fitting both. I've done this now for this sample of stars, and the models in the background now incorporate this. That kink is that point where you hit that critical Rossby number. And you can see that, still not perfect, but you do a much better job of simultaneously matching the open clusters and the astroseismic targets, right? And the kind of creepy thing is that the Rossby number you need to pick to make this work is the Rossby number of the sun. So very uncomfortable, right? You're saying something is changing at solar, right? And it's regardless of whether the sun's in the sample, like any way you try to get out of this, it's always the solar Rossby number. Okay, so you could say, well, why? Why should it do that? Why, maybe it works, but what physically is happening here that would allow you to do this? We don't actually know the answer to this. It's an active thing that we're trying to figure out. Anything that you change, like if you suddenly turned off the mass loss, that could do it. If you suddenly turn off the magnetic field, that could do it. The thing we think is the leading explanation right now is a shift in magnetic field morphology. So people that do MHD models of winds entrained in a magnetic field find that if you give the star a large-scale dipole field, it's much more effective at losing angular momentum than if you make that field a quadrupolar, higher-order field. Right? And there's two reasons for that. One of them is that the lever arm of a dipole is just bigger, so it's more effective. And the other is that quadrupole has more closed field lines, and so if you don't lose the mass, you can't shed the angular momentum with it. And it's like an order of magnitude difference in the efficiency of angular momentum loss as you go from big dipole to a higher order quadrupolar field. Observationally, we have the beginnings of hints that this is actually what's going on. I'll show you a couple of things later that kind of goes along those lines. So that physically is kind of the scenario we're working under. We're saying we suspect that around middle age, solar Rossby number, stars undergo some kind of transition in their magnetism where their morphology shift and angular momentum loss becomes very inefficient. This is not super uncomfortable when you keep in mind that the sun itself, over its cycle, shifts its magnetic field morphology. Go from something that's dipolar to something that's a quadrupolar and dipole every 11 years, right? So not too uncomfortable to say you might have a shift in field morphology. All right, you can say, okay, fine, but surely if this is a global shift in field morphology that happens for all stars midway through their lives, you obviously must be able to see this happen in more than 20 things, right? Where is all of the evidence that should be sitting there? So we spent a bunch of time now trying to go back and look at things, knowing that this might be there. So this is that rotation distribution I showed you of the full Kepler field in the beginning, where you'll notice the sun is right on the edge of this distribution. It's a longer rotation period. And we said, well, is that what, naively interpreted, right? Stars have a tendency to move upwards in this diagram as they age. The temperature doesn't change very much, period gets longer, right? So naively interpreted, this says there aren't many stars in the Kepler field older than the sun, which Kepler field is old, that's not what you'd have expected. But we can do a better job. We can quantify it and say, okay, let's take a population model of the Kepler field that gives us the range of ages you would expect to see, the compositions, the masses, push it through a rotational evolution model. And that distribution should have looked like this, right? So the color coding here is the age. Old things are at long periods. Young things are at short periods. That Kepler distribution fell here. And you can see there's this kind of glaring, set of stars that should be rotating slowly, but don't seem to be there. So I just spent, a bunch of time telling you about weakened magnetic braking. Weakened magnetic braking would tend to bring you up, but then stall you out, right? Because you spin down, but then you stop spinning down. You just kind of hang out where you were. If I institute a weakened magnetic braking model in this population model, I get something that looks like this, which does a decent job of matching the edge. This is with a Rossby number chosen to match the seismic sample. You can play with this a little bit and get the edge to move and match exactly if you want. But there's an easier explanation, right? You could just say, well, all those old stars are very hard to detect, and all you've done is fooled yourself because it's a detection bias. They're all quiet. If you took the sun and observed it with Kepler, you may not necessarily detect its rotation period. right? They're quiet stars. You can say, okay, what if it's just a detection edge? The way that we would normally, because most magnetic phenomena in stars are tightly correlated with Rossby number, amplitude of spot modulation is no different. So the amplitude of spot modulation increases with decreasing Rossby number. We could say, well, let's just pick a Rossby number and say, beyond that Rossby number, things get too quiet, I can't detect them. If you do that, you can get a distribution that looks like this, but you still need it to be something happening. Your detection edge needs to be at the solar Rossby number, again, which is also still uncomfortable. So something's up, right? Either spots are suddenly becoming rarer, there's the, we just happened to build a telescope whose detection edge was exactly solar, or we have weakened magnetic braking going on. What we really need is a set of stars who we don't necessarily need to detect their spots to tell what their rotation periods are. V sin I is out, it's too hard, they're all too slowly rotating. You can use things like calcium H and K, chromospheric activity indicators, but that's also still magnetic activity. One of the places where we really think we've got a nice sample is to go back and look at the seismic sample again. So the seismic sample, a rotating star, you have some modes that are moving, you have waves propagating with and against the sense of rotation, which gives you rotational splitting. You can measure that rotational splitting and get an independent measure, the rotation period of the star. It's very sensitive. It turns out to be the case that those modes, they spend most of their time near the surface, so it's sensitive to the surface rotation and not the interior rotation in sun-like stars. Those guys live here, right? So the ones with extremely large error bars have either ratty data sets or extremely small rotational splittings, and so the uncertainties are very large in them. But you can see the ones that you measure sit right along this edge. So if it were the case that it was literally just a detection bias that was the problem, you'd expect this seismic sample, which spans the age of the Milky Way, to fill in this gap more fully than it does. So instead of looking at it in this space, I can put them on this diagram and show you in period age. So the model in the background is the same. The seismic stars, about, I think it's a third to a half of them are overlaps, but now their periods come from not spots, but an internal seismic measure. It looks like this. So again, it looks like that you've probably have weakened braking going on. So Nick Saunders, who was actually here a couple of weeks ago, is tackling this problem. He's actually, because you end up introducing quite a few parameters to the problem as you go through this, it gets slow to do the fitting. So he's actually developed this whole neural network approach where he's using a neural network as a way of interpolating in a model grid. It's lightning fast. It allows us to explore a wider range of parameters to better treat the uncertainties on each individual star, because each star has its own set of parameters, and then you have population level parameters from the braking law. You'd like to do a hierarchical Bayesian analysis, doing lots of evaluations. This makes it super fast. So this is the early results he's finding is nothing surprising. It looks pretty much like exactly what you'd expect and what I've been saying, but he's doing this in a whole nice, complete, self-consistent way, and you should keep your eye out for it. It's coming out pretty soon. All right. So another place that you can say, well, that we've focused on the main sequence, but maybe there's other places where it's actually better to look. And the answer to that is there are. So this is what I'm showing you here is a HR diagram, and the color coding is the difference you'd expect to see between if you had a standard model for the rotational evolution and a weakened magnetic braking model. So here, the lightest green is like a 50% difference in the rotation period, and the black is no difference in the rotation period. And we've been living here, right? So we're picking up things whose rotation periods are like 20%, 25% different than you'd expect them to be. But really, the subgiant branch is where this signal is maximized. And that's because you've had an entire half of a main sequence to accumulate a difference between these two predictions. And then on the subgiant branch, where you start breaking again depends on exactly what your Rossby number is in the two cases. So you actually get quite a difference between the two models. We have been poking around, picking up subgiants that we can study well. We have one. This is 94 Aquarii A, case I'm going to show you here, that has astroseismology. It has cycles from calcium H and K. It's got all the data that you'd like to have. It's extremely well characterized. And if you take a standard model of evolution, you'd say it should have a period of roughly 80 days. If you took a weak into magnetic braking model, it should be almost half that. And the calcium H and K chromospheric rotation rate comes in at something that very much agrees with this. Now, I'm being a little unfair here because I can torque the stellar evolutionary models and change assumptions about convection and move these guys around. But in any prescription, the standard case comes in longer than the weakened case, and I can move these guys around a little bit. So this is indicative. All right, so I said this is a magnetic transition. Why aren't we looking at proxies of magnetism? What can you see if you actually go and look at the magnetic fields of these stars? So we just put out a paper a couple weeks ago about a pair of objects. This is 88 Leo, which is an object that should be before the transition. The transition is, roughly solar. And then Rho CRB, which is after post-transition. And we have spectropolarimetry of both of these guys that allows us to measure the magnetic field strengths and morphologies. When we look at 88 Leo, it is a strong dipole magnetic field. When we look at Rho CRB, it's consistent with a much weaker quadrupolar field. And so that pattern that we predicted holds up when you look at these two stars that straddle either side of this gap. What we'd really like to do is pick up things right near the transition and see how that transition happens, what the time scale is, right? And that's an ongoing process. You could say, okay, what about chromospheric activity? When you look in chromospheric activity, you see nothing. It looks completely smooth. There's no transition, there's no hint of it. This is the solar twin sample that Diego Lorenzo Oliveira published, right? And you can see it's just nice, smooth relationship. No kink, nothing. Why? So in this picture, where what matters is the large-scale dipole magnetic field, right? The chromospheric activity doesn't necessarily care too much about that large scale. It's sensitive to all scales of the magnetic field and smaller scales. So if you're doing something that's suppressing your dipole and turning it into a quadrupole and concentrating your field in smaller scales, you wouldn't necessarily expect to see any difference in the chromospheric activity if it's just a large-scale dipole that's weakening. So it's actually, despite the fact that it doesn't look consistent with what we're saying, we think it is. All right, and finally, you might say, well, is there anything interesting to be seen in cyclic behavior in magnetic dynamos? So this is a collection of stars that have magnetic cycles analogous to the sun's 11-year cycle in the Mount Wilson survey. This is generally decades of data on these guys. These are the best cycles in the bunch. In the literature, people point out that there's two relationships, two lines you can draw. There's some hand waving about them being different dynamo mechanisms. Some of these stars are actually, a cycle period is detected on each branch, right? So some of these guys are duplicates. And what makes people uncomfortable is that the sun is, again, like hanging out in the middle, right? And there's all kinds of arguments about if the sun were a Mount Wilson survey star, would we detect its cycle? Maybe it's just a detection bias, right? But it bothers people, and it should. Not all of these guys are solar. So here, the blue ones are F stars, the yellow are G stars, and the red are Ks. So you can see, actually, we have nothing in the Mount Wilson survey sample that's a period longer than the sun. That is a G star. All those stars are K stars. And I can add some upper limits here. These three stars have beautiful data. If the cycle was there, we should have been able to see it. It isn't. I can add some solar analogs to this sample. So 18 SCO, Alpha Cent, and 16 SIG all have seismic ages. So we actually know the timeline for this. And I could actually draw a line that connects them that's chronological. So these guys are all young sun-type stars. 18 SCO we know is younger than the sun, which is younger than Alpha Cent, which is younger than 16 SIG. And this kink is at a Rossby number of 2, the sun's Rossby number. So maybe we should consider whether or not there's something that happens to the cycle period as well. In cooler stars, that kink should happen later because they have deeper convective envelopes, so they hit that same Rossby number at longer period. And in hotter stars, it should happen earlier. And so if we look at the cycle periods of these stars, we should see this pattern borne out with enough of them. What we'd really like to have is ages for these objects, right? So we can actually place a chronology to where they sit on this diagram. Yeah.
What about the ones that break the pattern? Like the red hockey stick or whatever.
These
There
guys.
are still, yeah, K-forms that are that misidentified cycle periods?
I'm gonna wave my
Are they
hands.
funky?
Yeah. So it could just be some of them, and I don't remember which ones actually, have a cycle in both places. So it's just a secondary cycle. But I don't think that's the case for all of these. And I don't have a good answer for you, right? This is very skeptical, this thing, right? Yeah. Go ahead, Ruth.
If you doubled the cycle period of the sun, would it fill in that top line?
No.
Okay.
Yeah. And the sun has a secondary cycle, and it's like down here. It's below the other one. So it's really uncomfortable. Okay, so it suggests three things we can do and are doing at the moment. One is for stars that have existing astroseismology, we already know their age, we're going after their cycles with long-term LCO monitoring. For stars where you already have a cycle and decades of data on it, we're going after astroseismology with tests. So we can fill this out and actually put a timeline to these things. And then finally, we're doing direct measurements of magnetic field strengths and morphologies from the ground to actually look at stars on either side of the transition and do more than just say with a handful of objects, maybe this is what's going on. Okay, so I want to just kind of summarize where we are by going back to this plot. I've argued that things in here, basically gyrochronology works, right? Period-age relationships, we pretty much understand them. They seem to be pretty well behaved. And here it's probably okay to go ahead and use a rotation period for a star to get you an age. We have some code to do it. My same graduate student that's been working on the neural nets has built this code Kiyohoku that takes inputs like rotation period and stellar parameters and will spit an age back at you. It doesn't do it, it won't stop you from working in any of these places necessarily. So you do have to be careful about where you try to play this game. But we have an existing public package out there where you can go and get ages from rotation. Here, I've argued that rotation is not such a great age diagnostic, right? If your star's not spinning down anymore, it's not telling you about age anymore. It's giving you a limit on the age, but not a precise measurement. But what it is telling you is something fundamental about the magnetic field of that star that has changed. And so here, you're really getting insight into magnetism that we didn't have before by studying those stars. And then there is still this region over here where I argued at the very beginning of the talk, this is where you really want this to work. Nothing else works for ages over here, really. Apart from, kinematics can give you a bulk statistical age, but for an individual star, rotation or activity age relationships are probably your best bet for precise age. So we really like gyrochronology to work here. It's also where we have fewest calibrators. And the calibrators we do have, some open clusters, kind of down here, have shown us that it's not quite so simple over there either, right? It gets more complicated. So we have a bunch of ongoing projects to try to solve that portion of the diagram as well, focusing on the older stars. We've been working on an M67, which is a 4 billion-year-old cluster from the ground. We have a rotation sequence. It's not ready to be thrown up and recorded yet, but we have one, and it's super interesting. That paper is coming soon. We've been looking at binary systems where one of the binaries you can do astroseismology of, but the secondary is an M star, right? So you suddenly have an extremely precise age for a field M dwarf that you'd never be able to get any other way. And then we also are looking at large sets of wide common proper motion binaries that have a white dwarf or a seismic target or any age datable primary star where the secondary is an M, where you can take the age of that system, apply it to the M star, and try to figure out what's going on for the old objects that you'd really like to get ages for. And that's work by both a student I've been working with at UH, and actually a high school teacher from Lanai has been helping with this portion of the project. Okay, so with that, I'm going to leave up this summary slide and take any remaining questions. And thank you all for listening.
We have a question from Matteo on Zoom.
Hey, Jan, this is Matteo. Thanks so much for this super interesting talk. I think you made a very strong case for this transition in magnetic activity or magnetic geometry in stars or a certain Rossby number. And you mentioned a few proxies to explore. this possible transition and how really it connects to the physics of these stars. And I was wondering, you mentioned chromospheric activity. You haven't talked about things like flares, and I was wondering if you think there will be some interesting information in looking at the flaring properties of these stars, and if so, if you have done that.
We have not done that. I think there is interesting information there. So some of the challenge is that you tend to lose the flares earlier than you lose other diagnostics of activity. So you'll detect the rotation for longer, where longer is like going from active to less active. You'll see the flares will kind of peter out. You know, we don't really get many flares detectable around stars that aren't really rapidly rotating young things. So you'll have some challenges to face in terms of statistics, I think. It's not entirely obvious what you expect to see. There has been at least one paper that has proposed that by going through this transition, you actually, and the details of it, I'll admit, are a bit murky. I can send it to you if you're interested. That they argue that you might actually be able to store enough magnetic energy for super flares more effectively past this transition than before it. And so paradoxically, in your magnetically quiet future, you also put off more super flares than you would otherwise. That's if you buy that we're actually seeing super flaring G stars in Kepler to begin with, which, so yeah, I think it's definitely worth looking at. I think there'll be some challenges there that are distinct from the rotation or activity or chromospheric activity side, but definitely something to look at.
Thank you, Jen.
Maybe this is what you meant by calibrated, but I just want to be sure I understand a very simple question. So if you estimate ages by a period, a cluster, you compare the turn-off age, or they're the same?
Yeah, it's the turn-off age. So it's the turn-off age of the cluster
but then
is.
But then if you use one cluster, you can then extrapolate to another cluster, and you always get the same turn-off. You have correlation between turn-off age or agreement between turn-off age and age from the rotation of the stars.
So we don't generally actually have that many clusters. Like we don't have many clusters that we can span. So if you had two and you've done a good job on the calibration, if you calibrated on one cluster, you ought to get the same answer for the other one in terms of turn-off age. But we don't usually have that kind of redundancy in the cluster sample that we have. What we do is we take that turn-off age and decree that this is the age of this sample, and then force the period-age relationship to match it. And so it's constructed that way. One thing that we are worried about, two things we're worried about. One is that our cluster sample is almost entirely solar metallicity, and we think metallicity should matter for the spin down. Certainly in the structure of the star, but possibly also in mass loss itself. And so we don't actually have much information in the metallicity dimension. So it could be that you could take two clusters, same age, same everything, different metallicity, and it doesn't work. The second thing we worry about is that there is some evidence that the cluster environment you're born in will affect your initial rotation distribution, especially in young clusters. There are a handful of very populated clusters who have rotation periods that just don't match up with other clusters of the same age. And you can take, for example, like Upper SCO, which is 8 million years, you can evolve that forward and hit the Pleiades, no problem, under a standard breaking model. But if you take H-per and try to do the same thing, it doesn't work, right? So there might be actual differences in the starting conditions of clusters, depending on their environment and how populated, how rich that cluster was, that we are not accounting for at all here. So it's less of a problem as you go later and you forget those initial conditions, but it's a problem for younger stars, right? If there's some variation in the initial starting conditions from system to system.
Thanks, that's more than I wanted to know.
Sam?
So you mentioned this population of stars where you have like gyrochronology and you're trying to get astroseismology now, but essentially the astroseismic signal and the magnetic signal are inversely correlated.
Yes.
Is that like how large is the sample of stars where you can actually hope to do that? And is it larger than, say, the sample that you have with Kepler now?
Yeah, so we're not super concerned about that, because the real place where we need more data and this transition point is in quiet stars. And so if we really want to pick up a bunch of things, are you talking about or maybe I'm misinterpreting. Are you talking about these guys over here? Or are you talking about?
So you have a plot with or you had one slide that has like it showed tests on it, and you're talking about using, getting astroseismology.
Oh, okay, yeah, all right. Yeah, so most of those targets, for the vast majority of them, should be pretty old and pretty quiet, the ones we're really going after. The ones that the ones that aren't old and quiet are ones we already know the astroseismic detection is there, and we're going after, they're things that live here. These guys, things that live down here, are the ones we're going after cycles with now. And they're ones we already know have seismology, and they would be the ones that might be stabilized against pulsation by their magnetic fields, but we already know they're pulsating. The ones over here are the ones we want to get astroseismology for. They should be quiet already, so we're not too concerned about that. So, yeah, I think that answers.
Yeah. Thank you.
Okay, so we're a little past 4:30, but we also started late, so let's get the last couple questions in. So, Jackie, could you go ahead?
Yeah, can you hear me?
Yep, I can see you too.
Hi, Jen.
Hi, Jackie.
Question, which I may have missed it, but I was wondering what the updates were on calibrators that had a white dwarf with them. I know you had a student working on that when we were in Hawaii.
Yeah. So the update is that the white dwarf ages have been challenging, and they've been challenging because it turns out that the M dwarf, which this is never a problem except here, the M dwarf is too bright. And it is the photometry you need to do a good job of getting the white dwarf mass to get the age has been contaminated by its incredibly bright M neighbor. Right? So the white dwarf's like 2 magnitudes fainter than the M star, and the M neighbor, there's like diffraction spikes and stuff that's messing up the photometry. So this is in collaboration with JJ Hermes and Tyler Hines at BU, and they're working to help us get this problem resolved. It's very solvable, but it's a problem we realized later in the game, that this is basically contaminating our age measurements. But we think we have a sample of about 100 things now that look like they're going to have good rotation periods, and we're just trying to get the ages in before we can actually interpret what it's telling us.
Can I just ask follow up? How are you doing the ages for the white dwarfs? Is JJ using some approach? He's
using a combination of cooling tracks and one of these published initial final mass relations. His student Tyler has done a bunch of work on quantifying with white dwarf binaries how good those cooling age relationships are, and he's found some interesting patterns as a function of mass of the white dwarf. I think that paper is almost out, so you should keep your eyes open for it. It's a really nice piece of work, but it's been mostly doing due diligence to really understand that age scale that has been slowing us down a little bit, but it's very important stuff to be doing. So that's where we are on that.
Right.
Well, good.
I wanted to ask, you make a very convincing case that the deviation from the traditional braking relations is magnetic. But in the middle of your talk, you said it could be magnetic or it could be something about winds.
Yeah.
And I'm curious how much we know about evolution of winds of these sort of stars through their lifetime.
Yeah,
Is that a route that you're investigating, or is the magnetic case so sealed up? You're like,
it's certainly not so sealed up. I should actually include this plot. This is where I'll tear apart the confidence I've spent an hour building. So if you look, the way we do this is we say that m dot is proportional to Lx from the Wood, astrospheres work, and it's like I think it's half a dozen stars and like a power law, right, just drawn through them, and that's what we do, and that is not necessarily the right answer. You could do something much more sophisticated. You could envision a whole different set of ways of scaling it with m dot. M dot is pretty important for this. So it very well could be that it's not really just morphology. It's deeply embedded with MDOT as well. And it's probably, in reality, it's got to be some combination of the two, because they interact with each other very much so. So I've painted this picture that I think it's magnetism, but MDOT is definitely still in the running for it.
I mean, is that a data set that'll get better?
Say again?
Is that a data set of 6 stars, will that get better?
This is probably not, because we're about to lose Hubble, and you need Hubble to do it. So it's a little bit more than 6 now, but there's no obvious immediate future improvement to it that I am aware of. Do you have one?
No, I have a crazy question. That's
Yeah.
probably a stupid idea for 10 different reasons. But could you do it in the radio? If most stars have planets and you had a massive radio telescope and you measured the radio signal from the wind interacting with planetary magnetospheres.
So you need,
what do you need for that? Like fast times 100 in collecting area?
I mean, probably. I'm imagining this must be a stronger signal as you take planets that are close to their stars. You don't want those ones, because you don't want anything with the planet to really perturb the structure of this flow. So you're gonna want distant ones, which presumably means the signal is gonna be very small. So it's probably incredible sensitivity and luck to get a sample that's large enough with distant planets to do it, I'm guessing.
It's down there.
I had to guess.
I think there's like 1 or 2 claims in the literature.
Yeah, of this kind of interaction. Yeah. I mean, the people that are doing the MHD modeling of the winds many of them are spending, more than half of that effort trying to understand how those winds are interacting with nearby exoplanets. So the models are there. I just don't know what the models say about whether or not you could see this.